So we're going to do a free response question together. And our free response question is from last year's National 2019 FRQ 1. So if you can't see it well on screen, I know it's a little bit blurry. You can look it up. It's 2019 AP Physics 1 FRQs. So here we have, I'm going to zoom in a little bit. Whoop. Alright, here we have a kind of kinematics. Let me make my pen smaller since I zoomed in. Kinematics, forces, and then it's going to throw in a little bit of angular momentum at the end. So this is a good indication of the type of questions you'll see. I especially think that for this year, since you're probably only going to have 2 or 3 free response questions, that you will see questions that incorporate multiple topics. Remember, our topics are kinematics, forces, energy, momentum, rotation. Simple harmonic motion kind of goes in with rotation and forces. Technically a different topic, but you're going to see questions, I'm predicting, that are going to have multiple topics because they're trying to squeeze in everything they can into probably 2 or 3 questions this year. You have 45 minutes for your AP exam this year. But here we have 2 blocks. Blocks 1 and 2 are placed on a horizontal surface at points A and E respectively. The surface is frictionless except here. So here we have no friction, except for at C and D we have friction. So from A to B, we have a constant force applied to the block by this plunger. So here there is a force being applied. Then upon reaching B, it loses contact with the plunger and continues moving. So here there's going to be no force. Block 1 collides with block 2 at E. So here is also no force. And then here there's no force. And they collide. Well, they're stuck together. So basically, block 1 is being pushed by this plunger from A to B. Then plunger goes away from B to C. From C to D, there's friction. And then from D all the way to F, there's no friction anymore. So we're sketching the speed of the center of mass of the 2-block system as a function of time all the way until our block gets to F. So let's kind of think about it before we draw it. I like to make notes on the side, especially if I'm doing like a real free response question, to have an idea before I actually draw. Because this is going to be worth 5 points, just as a thing for the free response question. This is a 7-point FRQ, and this graph is going to be worth 5 points. So let's try to dissect it a little bit before we draw. If there is a constant force, are you accelerating? And Newton's second law tells us that yes, if you have a force, your object is accelerating. Or our object specifically will be speeding up because that force is pushing it in the direction it's moving. So that force will be adding to its velocity, or it'll be accelerating. So I know from A to B, I expect acceleration. So this is A to B. From B to C, there's no more force. So if there are no forces acting on your block, now we can revert to Newton's first law and figure out that, well, if there's no forces, it will continue in motion. So from B to C, it will have a constant velocity. Scroll down a little bit. So from B to C, there will be a constant velocity. From C to D, there's friction. So that's going to be a force see it's moving this way, there's going to be a force in the opposite direction of its motion. So that means we're going to have like a negative force, or we're going to have a negative acceleration, or our object will slow down. Because the only force acting on it will be friction. Friction always opposes motion, so our object will be slowing down from C to D. And then we said from D to E to F, there's no force. Our boxes collide, but from D to F, we're going to have no force, which is going to mean constant velocity again. So how do we draw this? Well, let's think back to what we reviewed about motion graphs. Hello, welcome, Andrew. Let's see. So from A to B, we have a block that is accelerating. So how do we draw that it is accelerating? Well, it's a constant force, so that means we're going to have a constant acceleration. Now, this is a speed graph, or similar to a velocity graph, which means that if we drew this is going to mean constant speed. If we drew this means zero speed. So what kind of line are we looking for if we're looking for a constant acceleration? And that's going to be a line that slopes upwards. I'm going to do my best to draw a straight line. That looks straight. If your line does not look straight, I recommend you use like a ruler or something, or I could cheat and use like the shapes. But I have a student that always writes like, this is supposed to be straight. If you're really bad at drawing a straight line, welcome, Jackson. So yeah, that is how we're going to show that our object is speeding up. Our speed increases at a constant rate. Then from B to C, we have a constant velocity because that force is no longer being applied. So how do we draw that? That does not look straight. Maybe I'll try again. Ooh, that's better. It's really hard to draw straight lines on my tablet. But there is our constant velocity, or constant speed from B to C. Then from C to D, we slow down. So what's that going to look like? It doesn't matter exactly how far you go down, maybe to here, maybe to here, but our object should slow down at a constant rate. So we should have a straight line to show a constant acceleration, and that acceleration is going to be negative. So maybe we go down, that doesn't look quite straight, I'll try again. Ooh. There we go. Ish. Kind of connect this right here. All right, so there's going to be our slowing down. So this is going to be speeding up, constant speed, slowing down. Then from D to F, there is no force. And I just want to recap here, I don't know if I mentioned this, that we're drawing the speed of the center of mass of the system. So basically we're drawing what's happening to the system. And at first, block 2 is just stationary. So block 2 does not contribute. But at E, block 2 does contribute. But when we're drawing the center of mass of the system, or the speed of that center of mass, we're basically only looking for external forces. So from E to F, they collide, but that force is considered internal to our system because our system is block 1 and block 2. So this is another kind of tricky way that AP exams are going to change the question a little bit. If we were drawing a graph for just block 1 or just block 2, we'd have a different answer. Maybe I'll draw that just to show you. But for block 1 has a force between 1 and 2. But if we're drawing the system, the 2-block system, the collision between them is not an external force. So what that means is we have a constant velocity here from D to E, And then we're also going to have a constant velocity all the way to F, because we are drawing the system and that collision is internal to the system. So if we were drawing this just for block 1, we would have a decrease in velocity here because block 1 slows down. If we were drawing for just block 2 would not move, and then it would move. So their total system velocity is the addition of their two velocities, so the system velocity is going to be up here. That was a really big missed part when this question was on the national exam last year. I want to say very few people kind of got that the collision between 1 and 2 is an internal force to the system. So this was 5 points. Basically, you got 1 point for drawing this sloped line here with a positive slope. You got 1 point for drawing this 0 slope line. You got 1 point for drawing a negative sloped line from C to D. 1 point for drawing D to F, all horizontal. And then the 5th point is that your graph is continuous, except if you messed up and you put that the velocity would decrease at E, except at E, if you made that mistake, you could still get that point. So what that means is when you drew it, like maybe I'll draw a second one. You didn't have it go here and then it go here, and then it go here. So your graph basically all connected with each other. Like this is one continuous line all the way around. The only exception to that is if you drew that it jumped down here, you could still get that 5th point. So how we feel, we're quiet. How we feel about this motion graphs? Do you think you would have gotten this FRQ? This one's fairly generous. 5 points for drawing a motion graph, where there was only one kind of tricky part of it. What do you think? Give you a sec to decide. If you want to type something, let me know you're still watching. You feel pretty good about this? Thumbs up? Nice. So this question so far incorporated forces and kinematics. This question's part B. Oh, I love this. Good. I felt good about this. Very nice. You didn't forget everything you learned in the last 2 weeks. I'm impressed. But the question kind of takes a separate dive here in part B. We start getting into angular momentum here in part B. So this is a good example of how the national exam throws together 2 or 3 topics in one question. So now we can change the plunger back to its original position and we take the blocks away. We replace the blocks with a sphere. The sphere is pushed by the plunger from point A to B with a constant force. So here there's a force. Then it loses contact, so then there's no force. Then there's friction here in the highlighted area. And then there's no force again over here. So kind of a similar scenario. There's just no second block. But there's a force from A to B. There's no force from B to C. There's a force from C to D. There's no force from D to E. the sphere loses contact with the plunger at B, continues moving across the horizontal surface towards E. At which intervals, if any, does the sphere's angular momentum about its center of mass change? Check all that apply. So where does our angular momentum change? Well, let's take a look at what angular momentum is. There's two equations we learned to find angular momentum. I omega, or change in angular momentum, is torque time. So those are our two equations here. So where does our angular momentum change? Well, where do we have a net external torque? So we're going to have a net external torque from C to D. You just found the chat. Yay! Good job. So from C to D, we have a net external torque. Why? Well, remember, torque is force times radius. So where do we have a force being applied at a distance from the center of the object? That's going to be from C to D. So friction provides a net external torque and reduces our angular momentum, or our angular momentum changes. So this was 2 points. And basically that you referred to that you were looking for somewhere that had a net external torque, and that friction is the force that provides that torque. So one place here that some students did lose points was just saying that there's friction from C to D and it slows down. And you have to mention torque to get points. So that is 2019 question number 1. We're probably going to be going through all of the 2019 free response questions